Hi. Maneta is an assistant professor at the University of Montana, Department of Geosciences. He got his PhD in 2006 from the University of Extremadura, which is located in western Spain near the border with Portugal. His research was co-directed by collaboration with Utrecht University in the Netherlands, and he was a student in the Environmental Resources and Sustainable Development program. His PhD research focus was the development and application of three-dimensional physically based hydrologic models, and specifically, he was interested in the spatial and temporal patterns of soil moisture and runoff generation in degraded semi-arid regions. Marco moved to the US and UC Davis for his postdoc. This is where he got interested in integrating economic models with watershed models in order to optimize agricultural production and investigate connections between water availability and poverty in Brazil. And he started a faculty position in Missouri in 2009, and since then has been investigating how changes in ecosystems and irrigation diversions are influencing the availability of water and energy across the landscape, especially in the mountains. Okay. So without any more ado, I will have to introduce Marco.
Thanks, Rob, for this very nice introduction, and thank you guys for attending this seminar. Here is definitely better attended than the ones in the University of Montana. Yeah, as Rob said, I'm a hydrologist in Missoula, and much of the activity that we have in our lab is concerned with the fundamental questions of hydrology, which at this point are related to understanding the fine details of the hydrologic cycle. And in that sense, hydrology has been traditionally circumscribed within the realm of geophysics. We've been using the laws of physics to understand and study, the factors that govern the movement of water in the landscape. But the major breakthroughs that we've had in hydrology in the late 20 to 30 years come from incorporating ecological processes and human processes into our understanding of the hydrologic cycle. And in that sense, modern hydrology and the kind of hydrology that we do in our lab is inherently very interdisciplinary, and understands that ecological human processes are a fundamental part of the hydrologic cycle. Yeah, so in that regard, I want to acknowledge the IOE for supporting the activity of my lab, either directly or indirectly, by several projects that have resulted in a couple of very nice simulation models, computer models that I want to bring to your attention, and we're happy to share if you guys are interested. The first one is a eco-hydrologic model that we call ECHO, and this is a model that was designed to conduct water studies in forested regions. This is a spatially distributed physics-based models that solve an energy balance scheme and a water balance scheme coupled together, right, to understand the interaction between water and energy. But the novelty about this model is that it integrates a carbon uptake and vegetation growth component. So you can use this model to study long-term interactions between vegetation growth and how vegetation reapportions the energy and the water into the different components of the mass balance. So the second model that we've been developing is a hydroeconomic model that we call data simulation, water use and agricultural productivity to do what. This model supplements the first one because this model is designed for water studied in agricultural regions. So the model is applicable when the economic decisions that farmers make impact the water resources, often more than environmental impacts, right? So water farmers decide to allocate land to different crops and apply water to different crops, right? And that has an impact on the hydrologic cycle. So it's a behavioral model. This model simulates the economic behavior of humans, right? And makes use of remote sensing observations of economic activity to make sure that what the model does is actually consistent with reality. So those two models, and most modern hydrologic or environmental models have a hydrologic engine underpinning all of the processes. And those models rely on the concept of conservation, right, to work. So the typical implementation of the conservation of mass and energy is through this accounting equation, right? So the amount of inputs that we're getting into our system and the outputs equals the rate of change, right? That input within the system. This equation is really nice because it puts a limit on how wrong we can be with our calculations, right? Which is real good. On the other hand, the equation gets very involved quickly, and it's very hard to, harder than we thought to pin down, to constrain without observations. So the typical implementation of the second equation at the watershed scale, in the case of water, is the input is typically precipitation, right? And this precipitation needs to leave a watershed either as evapotranspiration or streamflow discharge. Now, the typical assumption that we make when we are applying this equation at the annual scale is that we are working with steady-state systems, right? So the rate of change in storage at the beginning and at the end of the year, pretty much are negligible. So in the case of conservation of energy, my input is the radiative forcing, right? My net radiation. And this net radiation has to be spent in three ways, either as latent heat, evaporating water, sensible heat, which would be heating the air, right? And heating the ground. So that's how you spend your radiation. And those three, all these terms have to balance out. So now the connection between those two equations can mostly through the evapotranspiration and the latent heat term. Now, what happens is that the amount of evapotranspiration you're going to have depends on the available energy that you have to evaporate water. But the available energy to evaporate water depends on the amount of available energy, the energy that you're going to allocate to the latent heat terms depends on the water that you have, right? So those two equations have to be solved simultaneously. And this is what modern hydrologic models are doing. And it's something quite recent, right? So this is providing us big advances. The thing is, other sciences akin to hydrology, like atmospheric sciences and ocean sciences, have seen larger advances than hydrology has seen lately. Why is that? Most of the world looks like this, right? So we have a atmospheric layer, right, that is on top of our oceanic layer. But the application of those equations in those settings is relatively easy because you have an unimpeded medium, right, where you can put a grid, right, partition that and solve your equation. And the boundary condition with the ocean is you can assume that it's fully saturated, so it's always energy limited. There's no water limitations, right? So the equations become a little easier to solve, right? So this contrasts with what we see in hydrology, right? So we have a much more complex geometry of the domain, right? And we have some areas that are fully saturated, like streams and lakes, but then we have some other areas that are saturated sometimes they are not, right? Soils sometimes are evaporation is energy limited, sometimes it's water limited. And then we have vegetation that changes all the dynamics of water and energy, right? And has roots that permit the atmosphere to reach water deeper in the ground, right? So all this makes the solution of this equation more complicated. But okay, we can deal with this. If the region is flat, you can assume that your boundary conditions, your atmospheric forcings are somewhat homogeneous in the landscape, right? So there's no very large variations in the amount of precipitation that you're getting in the amount of radiation. Now, when we move to areas of complex terrain that we have in western Montana, we have to deal with very steep topographic gradients, and we have to deal with very fast changes in the precipitation and energy inputs at very short distances, right? And this needs to be constrained. So how do we constrain the thermal precipitation? So we typically use ground observations. And if you look at this graph here, is the distribution of the snuttle sites that we have with more than 10 years of data. And most of the snuttle sites are located in moderate and low elevations. So we have about 2,300 meters. We have 3 stations. And not very main. You say, well, above 2,300 meters, there is not a whole lot of terrain. And this is true, but the amount of precipitation that is following this small terrain is much larger. So the amount of precipitation you get at high elevation is inordinate to the area. Even worse, those are areas that are in yellow and green there are the areas that have the highest interannual precipitation variability. That's where the biggest uncertainty in our precipitation inputs is contained. And this is where we have 3 stations. And at 2,500, 1. So we believe that this is causing, this bias in our observation system is very well documented. So we have a bias to where the process is happening at low elevation. So let's get back to how we typically constrain this equation. This chart is actually very well constrained because our streamflow system of measurement is actually quite reliable. See, this is the best information we have. Yeah, we cross fingers there. The assumption of steady state is actually good. And why not? So we still have to terms to constrain precipitation and evapotranspiration. And evapotranspiration is actually very poorly constrained. It's really hard to measure. So now, because we have measurements of precipitation, we have this not a network, right? So we trust more knowledge of P than ET. So we have some suspicion that we are underestimating the amount of precipitation that we actually have in our mountains. And this is going undetected by our models because we are compensating this by adjusting evapotranspiration. Since it's not constrained, you adjust evapotranspiration, you balance out the equation, and you move on. Happy, right? So that wouldn't be a problem if we are not being told that the hydrologic cycle is intensifying, right? So one of the effects, one of the consequences of climate change is that we have a intensification and speeding of the hydrologic cycle. So scientists tell us that drier areas are going to get drier and wetter areas are going to get wetter, right? The global scale. So this obviously might have important consequences for many environmental and human processes. So if you look at the regional scale, our region falls in the area of the Pacific Northwest that is supposed to see an increase in the amount of precipitation. Yeah. So the area where I want to start is not around Western Montana. It's not very far from the Pacific Southwest, where we're going to see decreasing precipitation. But yes, typically we are within the realm of more precipitation. So what does the literature say? You can see here, but it says a paper by Philip Mode that says that, yeah, so over Western Montana and most of the Pacific Northwest, we're going to see an increase in precipitation of about 1 to 2% annually, right? This other paper by Eric Salatier says that this intensification is going to be more relevant in regions of complex terrain like we have in Western Montana. So we're having more precipitation, although there is this very recent paper that came in December in Science that says that there is a decrease in the speed of the westerly, so the graphic precipitation is going to weaken, so we're going to have a decrease in precipitation. So it seems it's easier to put a car in Mars or bring a car to the moon than figuring out whether we're having more or less precipitation, right? We're still apparently kind of agree what's the sign, let alone how much, right? So yeah, but the general consensus is more. So this is what our model says. This is where like the bulk of the scientists think we're headed. So what's the physics? What's causing this increase? The physics are relatively easy. With climate change, right, the average temperature of the air is increasing, and as the temperature increases, its ability to carry moisture increases. And this is because the molecules within the air move much faster, right? They're more energetic. So the water molecules have a harder time crossing together, right, to form a drop and condense. So, right, so you can maintain more water molecules there, right? The relationship is exponential, but like I believe that for like about a temperature degree of increase will increase the ability of the atmosphere to carry moisture by about 7% more moisture. So the fact that the atmosphere carries more moisture doesn't necessarily mean that you're going to have more precipitation. You may have a system that has more storage in the atmosphere, right? There's more water in the atmosphere, but doesn't mean it has to slightly increase storage there. The thing is, in mountain regions, you are pushing this air up through orographic effects, and it's like squeezing a sponge, right? So you bring it up, squeeze the air, and just squirt the water out. If the sponge has more water and you squirt it, more water is going to come out, more precipitation is going to happen, right? So we should expect more precipitation coming. The thing is, the precipitation doesn't need to be distributed evenly over the entire elevation gradient. No, it might be happening high up on top. So what does the observation say? Because he said, well, like we should be able to test it because we have some observations, and this is true. So this is a famous paper by Phil Mode in 2005, and this paper it's been cited a lot in all the studies that look into the effect of declining snowpack over the western U.S. And what this guy did was study the dynamics, the trends of the amount of snow on April 1st over time and snow courses over western Montana, right? And what he saw was that in most of those snow courses, the trend in April 1st snow was declining, and this is what we see in the red dots, right? So we're having less snow. The fact that there is less snow doesn't mean that there is less precipitation. It may mean that you have more precipitation falling as rain, it's more and snow. But now, there is a lot of intriguing blue dots there that say increasing snow. So, and there's increasing snow, most probably it means that there is an increase in precipitation, right? So if you flip a couple of pages past that figure in the same word, there is like these two very interesting figures. This one here, the x-axis here shows the correlation between April 1st snow and air temperature. And the low elevation, the correlation is negative and relatively strong. So the more the temperature, the less snow in April, which makes sense, right? That's harder. But look, this happens at low elevation. As soon as you're starting to hit, like over 2,000 meters, the correlation becomes zero and sometimes even positive. More heat, more precipitation. Well, the thing is, more heat, more snow. So the thing is, when you get high up over a point, it's very cold. And if it is like -8C or -5C, it doesn't really matter. Like the precipitation is going to fall as snow and it's going to accumulate in the snowpack, right? So there's no correlation with changes in precipitation. So if you look at the figure on the right, this tells you where those blue dots in the previous figure are. This is a relationship between the snow courses and elevation, right? And then latitude. So where are my blue dots? At high elevation. We have an enhancement of the snowpack there. But now you say, well, but there is a decline with latitude. And the thing is, here, there is a lot of dots here because there is an oversampling in the Southern Sierra. There is very high elevations there. And that's where those guys live, and like San Diego Center and LA, and they just go the same way you guys go in your mountains, and they sample there the hell out of it, right? So, but as you're moving out, the number of sampling decreased. And look over Western Montana, we have like a number of samples, obviously. But if you look at the latitude of Montana, most of the sampling occur at 2,000 and below. We have plenty of area below, above 2,000 meters, right? If you use snow courses that have been sampling there about this elevation, they show an increase. If we had sampled more snow courses at high elevation, would that figure change and would show more blue dots? That's an interesting question, right? We don't know because we don't have enough measurements there. So this is for the entire Western US, which we don't care. We care about Western Montana. So what we did is we conducted some more research on that topic. And what we see here is on the bottom graph, this is the simulation of the precipitation field, winter precipitation, the one that is likely to produce snow, using a model that is driven by observations. So the model is called PRISM, we're using hydrologic studies. And what the model does is takes the ground network of observations and performs some kind of an interpolation and produces the precipitation field. This model here is a physics-based model, a regional climate model that is independent of the observations. And it just uses the physics to drive the dynamics of the atmosphere and produce the precipitation there. So both models have a remarkable similar description of the spatial patterns of precipitation, but they disagree on the amount of precipitation that is falling, like here in the Mission Mountains and in high elevations. So the mechanistic model, the physics-based model, says more precipitation up there than the physics-based model. And you may say, well, like models sometimes go bananas. Like they are badly parameterized and in the stream, right? Models are very complex and sometimes they don't work very well. But now let's look at something very interesting. This is the same information over the same area, but what we're going to see here is 5 cross sections, right? Over the studied region. This is Western Montana. And those are the 5 cross sections here. The black line is the topography of the cross section. The blue line is the precipitation predicted by the physics-based model, and the pink line is the precipitation predicted by PRISM. So both models tend to agree very well at low elevation. And at low elevation, we know that PRISM performs very well because there is a lot of stations there for the interpolation. But the physics-based model is not depending on the observations and performs there very well. Where they disagree is where you get to mountains, right? Now, the physics-based model says at high elevation there's no precipitation. So if the physics-based models perform well at low elevation, why should they perform bad at high elevation, right? We kind of, it might happen, but there's some chances that there's more precipitation. And there's also chances that PRISM is carrying the low bias from low elevation into the processes at high elevation, right? That could be possible. So the topic of this research that we've done is not whether there's going to be an increase or not. Like I don't want to have a crystal ball and predict the future and say, we're going to have this much precipitation. What I'm interested here is saying, if there was to be an intensification of the hydrologic cycle, if there was to be an increase in precipitation, would it be detectable? Could we actually observe it, see it with our current network of observatories? Because there's not outside, there's not a network. Is detectable for our region, the intensification of the hydrologic cycle. So how can we go about it? Well, we have two options. We can use our observations to study it, and just every single way as it has been done in the past. The thing is, our observations are, there are several problems. One of them is carry the bias that we told, most of our observations, it's not a random sample of the landscape, it's a bias sample, right, for many reasons. The other thing is regular observations tends to be relatively short. The third thing is that we don't have observations for the future, right? So what's the alternative? The alternative is to use mechanistic models. Mechanistic models use our best understanding of the physics that drive, like the dynamics of the atmosphere, right, over regions of complex terrain, right, and produce a precipitation independent from the observations. The thing is, mechanistic models have also downsides, and one of them is the complexity, the number of parameters that need to be tuned, right? So they carry their own biases. So what can we do about that? We can perform a statistical correction of those biases, right? And if we do this, what we're going to get is the best bias-corrected mechanistic model, information from a mechanistic model that we can use as guide information, independent of our observations. So we're not having observational bias. So now what we have with this setup is two different sources of information about the same process, and they're independent, right? One through observations, one through physics, right? Physics corrected with statistics. Let's make it the best possible, right? So what's interesting thing about that is we can use observations. We can use these two models to evaluate how good is our observation network to constrain the uncertainty in our hydrologic model, right? So we use that using Bayesian inference. So what we do is assimilate the observation into our hydrologic model. And what we get there is a posterior uncertainty that tells how much do the observation network help reduce the uncertainty in our model, right? And this will give us a measure of the value, the observational value of the network. So this is sort of like the grand setup of the method. So what observations we have, where we're going to conduct this research over Western Montana, they're in the square, and each of those red triangles is it's not outside, it's our network of observations that we have. Yeah. And what kind of model we're going to use? We're going to use the best we have available. So the most sophisticated, the state-of-the-art regional climate model now is the weather research and forecasting model. It's the WRF model. And what we do is we use this model to downscale a global climate model. And we chose PCM, the parallel climate model, which is a model used by the IPCC, a model that is known to capture well the decadal oscillation of linear stages, right? So we downscale using WRF PCM over this region. And we downscale hindcast simulations from 2000 to 2010, and we also downscale future simulations 2047 to 2046. So the mid-century horizon that is good for water management, right? Instead of like the 100 years. So what we do is we downscale that using WRF. We downscale PCM using WRF to 4 kilometer spatial resolution. And this spatial resolution is already good to capture much of the effect of the topography, right? Like orographic effects, right? And we're going to focus instead of the entire total annual precipitation on the precipitation from December to March, which is the precipitation most likely to contribute to the snowpack, right? This is what we call winter precipitation. So we have this set up, but we know that PCM has some biases, so we have to correct them. How do we correct them? So we need a benchmark simulation to perform the correction. And what we do is we use WRF again, but instead of downscaling now a climate model, we downscale a weather model. And the model that we use is the Global Forecast System, the GFS, which is an operational weather model that NOAA uses to produce the forecast, right? So what we use is the final analysis product. And this final analysis product starts a little later than the actual GFS because it waits for some radio sounds and satellite information to come, and it gets assimilated into the model. So we ensure that the model reinitialization every time you want to make a prediction is reinitialized with initial conditions that are consistent with reality, right? So we downscale work over Western Montana using the same resolution as the Dallas PCM, so we can compare them. So now, since the analysis, the FNL product, the final product, involves ingestion of a detailed representation of the atmosphere through, like radiosones and remote sensing, not SNOTELs. So we're still independent of SNOTELs, right? So we believe that DFS can be used as a reference to which correct the biases in PCM work. So do we have biases? So if we compare the frequency distribution of the precipitation between PCM and the downscale PCM set and the downscale DFS set, we see that, yeah, we have a high bias in precipitation and moderate and high intensity. So what we have here, this is the frequency, the precipitation of different intensities is happening. And here this is a log scale. So this actually 99% of the precipitation happens, it's like 40 millimeters a day or less. So PCM tends to predict a little too many events of high precipitation. So how do we correct statistically this? We use a quantile correction method, and this is a standard one after Piani et al. So I'm not going to walk you through the details of this, but yeah, it's basically a two-parameter correction on the cumulative distribution functions of the model that you want to correct and the benchmark. So what you do is you end up stretching. So you end up doing a correction. So the statistical distribution of the model you want to correct resembles or becomes the same as the statistical distribution of the benchmark, right? So when we run this correction, so the corrected new distribution of PCM work corrected is this green dashed line. So the correction over most of the precipitation is really, really good. Now we have a model that actually is believable. So we still have, now we're like underestimating a little bit on high precipitation intensity, but those events don't happen very often, and we don't believe it's going to have a big impact on the final results. So we have now a very good model that is bias corrected based on physics, right? That gives us the winter precipitation over the entire landscape, and we use this model to infer the properties of our the precipitation field, right? The interannual variability and averages and such, right? So if someone is going to ask us, how much is going to rain at a location next year, right? The best we can do is just give them the average of precipitation, right? This year is going to use the average, and your uncertainty in your prediction is going to be the interannual variability, right? If there is a location where every year rains the same, you give that average, you're quite certain you're going to hit it. But if the interannual variability is very large, you give the average, the expectation, but then it can rain, the year can be wet, can be dry, right? You don't know, and this is your variability. Now, if you wait for the year to end and you have observations, you can update this prior information, right? So let's imagine that this is not outside in that region and farther, or like someone asks you how much precipitation it is, and you have information there for that specific location here. You go and do the reading, and if it's not outside, it's really good. You say this is your amount of precipitation that you've had, or amount of snow. The same thing in this other location. But what if they ask you about the precipitation there, right? So if the weather in the top of the mountain is coupled to the conditions and the weather at the bottom of the mountain, right, you somehow can create some interpolation between the two stations, right? Weight, average, whatever, right, and get, like the precipitation up there. But if the weather on the top of the mountain is a couple from the weather at the bottom, right, the amount of information contained here might be like pretty much useless, because so the best information that you can give is the average and the standard deviation, right? So how do we calculate whether the information from here carries up here or not? This depends on the covariance structure of the precipitation process. What we use is Bayesian statistics with this. So let's imagine that for one location, it is similar. Let's see if I can go through this in a way that makes sense. So the prior information is we use that our model estimate. This gives us my average information for that location and my interannual variability, which is my uncertainty. So if someone asks me for this location before I have any observation, my current information, how much is for my rain, I can say 40 centimeters per month of rain. But your uncertainty is, some years rain more. It's very likely it's going to go higher or lower, right? So if we have a very a snow tail close by that is very good, like really reliable. And you wait until there is observations there, you can update your prior knowledge, right? And if you have a very peaked distribution on your snow tail, meaning the average is concentrated over like a point, there is no like error, your posterior estimate is going to be very close to your measurement. So the measurement is very informative, and the error in your estimate is pretty much the error of the snow tail at that location. So in that case, our observation there is very informative. We want to keep that snow side nice. So now let's imagine we go to a different location where my prior estimation tells me this blue line that there is like 45 millimeters, centimeters per month. And I have a snow side that either is broken, it has a lot of wind effect, wind undercatch or overcatch, or it's very far away, and the information doesn't carry very well, right? So you're going to have a snow tail that have very large error uncertainty. So when you perform the Bayesian analysis, you're going to see that your posterior precipitation estimate is very close to the initial precipitation estimate. Basically, it says that the snow tail observation is not very informative. Like the information in this snow tail side does not bear any relationship with the actual processes that we really happen at that specific location. So you say, observation there, the observation network does not provide information about the process at that point. So this is my prior uncertainty. This is my interanual variability. So I can give an average, and the best I can say is that you have a 68% probability. This is standard deviation here to be between plus minus those numbers here, right? So a low elevation on my valleys. So this is a different problem which will be run here, so if I get an idea of the region, right? So most of my valleys show very narrow, very low interanual variability. So you give an average and you more or less get it, right? You might be wrong by 80 millimeters up or down. But as soon as you go high up in the mountain regions, interanual variability increases, and you become more uncertain about the amount of precipitation that is actually falling there. What happens when we ingest all our observations there? Can we constrain this uncertainty? This is what you see here. This is the posterior uncertainty. And the truth is yes. So now you see that this is the same scale, so the colors are a little lighter now. So for low elevation regions, our uncertainty is really high now. So we will be able to detect change in precipitation with relatively high accuracy. But look, still in those regions here, we have a sizable amount of uncertainty in the order of 120 to 200 millimeters of play, right? So we give an average, but you still don't know if you're 200 millimeters up or down, right? Is that precision enough to capture the expected changes in precipitation? This is the question we were trying to answer, right? So what we do is we use just a standard T-pair student test between the average precipitation now and in the future, and use the background probability to see if the change is going to be significant. So we run two tests. One of them is whether there are significant changes in winter precipitation, right? If our model was right, like we're not taking into account now our observation networks. Where are we going to have changes in precipitation where the difference in the mean precipitation between the past and the future is statistically significant with respect to the background variance that we have, the background variability, right? So what we're trying to compare is whether the difference in mean is different than zero with a statistical degree of guarantees, right? Now the second test introduces the error that we have in our observations. Now what we're asking is, from all the places where from all the places in the landscape where I can assure statistically that there's going to be a precipitation change, which ones are actually observable with the uncertainty of our observation network? And this is the second test that we're changing there. So the difference that we're expecting between future and historical, according to PCM, is relatively mild over most of the region. Like in the order, so of like 80 millimeters or something. To at the mid-century horizon, and most of the difference is going to be in high elevation regions like the Mission Mountains, hitting the Ida Panhandle, south of Glacier National Park. So the percentage difference between now and the mid-century is more or less in tune with what the literature says. A little lower because now we're bias correcting these models, right? So we have a better representation of the actual change because we are performing the statistical correction. So the difference in change is going to be less than 1%, way less than 1% change per year, right? And at most it's going to be 1% at the place with the biggest change. So the change is very modest. Is it observable? So according to the model, the places where the change could be significant are those places with the dots at the 95% confidence interval, right? So there's something very interesting here. Those points are not random. You can observe statistically the changes in precipitation are statistically significant, or they are observable on the windward side of mountain ranges that have a north-south orientation. Basically, mountain ranges that are perpendicular to the storm tracks. And not only that, the mountain ranges that are, the leeward is facing a very open area, like the Flathead region. So there's plenty of other mountain ranges with orientation north-south, but they are getting all the dirty wind in the leeward side of the Mission Mountains, right? So the variability there is higher, so the uncertainty in your precipitation is higher. So any change has to be very large to be actually significant. So this front here tells what positions in the landscape you can actually take the pulse to the where you can notice, the change with some reliability. That's quite interesting. Now, how many of those points can actually observe? How many of those points are actually statistically significant when we take into account the observational uncertainty? It's really slow. We're missing. So that's where we can actually observe with a degree of statistical certainty that yes, so there is statistical change. So we're missing all this region here. We're vulnerable to missing those changes because of our lacking in observational capabilities. So topographic characteristics of the places that are really good for observing. So in terms of aspect, 68% of the domain of the studied region is oriented according to that gray area there, like mostly north and northeast. The orientations of the places where the variability, the background variability is low with respect to the change, we can see change that is significant has an orientation toward the northwest, sort of like facing the tracks of the storm paths. If we take into account the observational uncertainty, the orientations where we can actually detect precipitation change are even farther due west. You have to point really westwards, right, in order to be able to pin down the places where statistical change is going to happen. So this is in terms of the orientation. How about in terms of elevation? So the gray line in the background, the gray histogram here, is the distribution of elevation in the entire region. Now, the places where the statistical change in precipitation is going to happen is given by the blue line. So there's going to be a statistical change over the entire elevation gradient, right? So, and how about the places where we can actually detect it with that observation network? So we're missing change at high elevation. Our change is only detectable in westward slopes and moderate and low elevations. We're missing the ability to capture, to detect change in high elevation regions, right? We're missing all that. So, the student who covering this project says that one of the uses of that work is to, if we were to optimize our network to capture that process, you can use that. I don't find that all that exciting. What I find exciting is what are the implications of that change, right? So, what we're doing is a lack of available calculation here of what it means to not to observe or to be missing this amount of water. Most of the precipitation is going to happen in regions above the freezing line, even accounting for climate change. So much of this extra precipitation, if the prediction by PCM-WRF was to be correct, most of the increase in precipitation would happen above the freezing line. So what we would produce is an enhanced snowpack that we're not observing. And that would be the equivalent of 30% increase of snow. There's a lot of precipitation coming up there, or 1.7 billion cubic meters that we're missing, which is about 10% of the global runoff. So you may ask, hey, can we capture this precipitation change in the stream flow record? And a lot of people have tried to do that. The problem is, when you're having climate change and changes in precipitation, there's also going to be land use change, there's going to be human impact. So the evapotranspiration term that is not very well constrained will make it very difficult to attribute change in precipitation, change in stream flow to precipitation, right? So this thing is not very, very easy. So and the consequences are, like actually important because we have more water than we actually think we have. So I figure closing here. According to PCM-WRF, winter precipitation is likely to increase over most of western Montana, like a moderate, once statistically correct, it's a small, it's not a huge increase, but it is significant. So the statistical significant changes are generally on the windward slopes and mountain ranges that are not affected by the wind shadow of other obstructions, right, to windward, right? So these are places where we should be looking for the hydraulic intensification. So now the other big point is that the network does not have the accuracy to detect the expected change in areas at high elevation, and certainly in areas, not in areas that are not directly perpendicular to the storm, to the frontal flow paths. So those high areas where most of the and detected precipitation might be coming are areas that are likely to still remain below freezing, over the freezing line, right, even under future warming. So an enhanced snowpack at high elevation might offset the loss of snowpack at lower elevation, right? And that might have a confounding effect on stream flows, so complicating the interpretation of the stream flow signature, right? So yeah, the implications of misdiagnosing this trend in precipitation and the magnitude of the precipitation change, right? The big implications, the most evident, are for water management, right? So we might be making plans, like thinking that we have maybe less water than we have. But there is also important ecological changes, right? If we see greening in the higher elevations, right, we may be attributing it to like increasing CO2 to other things, right? Because we don't know that it might be more water there than we have, right? So plants might have more water than we thought first, right? So now, this study is not about whether we're having this amount of change as PCM tells. It's about whether we could detect it, right? So I kind of say that we're actually having a change. We might not, but we would not know it because we lack the observational capabilities. Thanks.
How much does a SNOTEL site cost? And the reason I ask is your not exciting application of your work was siting of weather stations.
Yeah.
But how much is a SNOTEL? How much would it cost for an extra 100?
No, I have no idea.
Wait, those are your tax dollars.
No, but even if it is on my bank account, I don't know where I spend my money. I don't even know what things cost. Yeah, I have no idea. So Brian DeMoncos is the guy running the SNOTEL network from NRC here, and it's stationed in Bozeman. He will for sure know it. And yeah, it might be worth like just spending a few strategically placed SNOTEL sites, right, to see, because this is important. Are we going to have more water, right, in the future, right? And that might buffer the impact that we're expecting of climate change. Right? It might be worth observing it. So you can do a cost-benefit analysis, right? The cost of placing a number of stations and how much you're buying in terms of increasing the precision. Yeah, that would be actually very interesting. Yeah.
You mentioned the loose paper with the decreasing westerlies.
Yeah.
How does that jive with your modeling of your results for?
Yeah, so I was talking to him the other day, and have you read the paper?
Yeah.
Yeah. So yeah, it's an interesting idea, and I think he very elegantly looks into those precipitation signals in the streamflow record, right? But then the thing is, he underpins that there's some basic assumptions that he is making about some basic assumptions that support the entire structure of his reasoning, right? And one of them is the speed of winds that is modeled, and if you look at the trends, they're significant at a very low level, and then there's a number of assumptions that So he claims that evapotranspiration cannot explain the change in stream flow, and therefore has to be a change in precipitation. And I don't think this is properly well constrained, because you say, well, like we've been using basins that do not have big impacts, like agriculture, but there's like many other impacts that are not agriculture, right? And there is like forest fires. There has been changing the structure of the forest, right? And there's been like many things, like, and in many papers that I've said, well, there's all this very many papers that say that evapotranspiration is going up over the entire Pacific Northwest, right? So how can you say it's not going up, right? So yeah, we have this very, yeah, that's how science works, right? So you put your work there and people will discuss it. And, yeah. But yeah, I find it very fascinating. Yeah, Jack?
Great stuff, Marco. So there's clear implications of changing snowpack at high elevations and the uncertainty associated with that for runoff and predictability of future projections of runoff. But a lot of the mid to high to lower elevations in this area are actually in the midst of a long-term increase in aridity. And actually, according to things like the Palmer Drought Severity Index, just a decline in actual good growing conditions. And a lot of the land area is predicted to have severe and increasingly long duration drought. So it would seem that maybe at the high elevation, the snowpack, while it's so critical for runoff, is actually irrelevant for much of the land area in terms of carbon sinks and biodiversity.
Right, yeah, it depends on, because yeah, water does not stay, well first, aridity index is not only the precipitation, it's also the extraction, right? So you can have plenty of precipitation, you have lots of extraction, you're going to be very arid. You can have a little precipitation, you have low extraction, you're not going to be arid, right? So precipitation is only part of the picture, and evapotranspiration is poorly constrained. The other thing is that, yes, so precipitation does not tend to stay in the place where it falls, right? It tends to run. And so yeah, you have the snowpack there, and you would expect that this water at some point is going to reach the mid and lower elevations, right? And there's a problem of routing. Now, if you have more precipitation, and actually, I'm working now, like discussing with ecologists whether there is an effect in vegetation at high elevations. What can happen is that there's more friction, more evapotranspiration losses as water comes down. There's more water, but there's more water and there's more wind, there's also more evapotranspiration losses. So the actual water that actually reaches down is much smaller, right? And then there's also the issue of the redistribution of heat by the onset of spring flows, right? So you can have a lot of snowpack, but if you melt it really fast, as soon as the soil is saturated, the vegetation is not going to see the extra water because the extra water is just going to flush out, right? So there's a number of issues, like that converge into the terms of the aridity that cannot be just simply explained by more or less precipitation. And the other thing is that we're talking about very small increases. We're not talking about doubling the snowpack, tripling it, right? So we're talking about, yeah.
I'm not sure if I can articulate my question, but so from a work model, it seems like it overestimates the amount of snowpack compared to like the PRISM model, right? And it's based on some physical, just the physics of snowfall and stuff like that. So if that's the case, then why can't you interpolate data from lower snowtall sites to higher sites if there's the physics of how snow actually falls? So what is there a different process?
Yeah, no, this is exactly what we do with WRF. We use WRF as an interpolator. So the Bayesian analysis that we have done is called optimal interpolation. And you interpolate with a covariance structure of precipitation. And that tells you how autocorrelated in space the precipitation process is. If the autocorrelation gets lost really fast, it's very similar to a kriging. So you have a variogram, right, and tells you how far your information from a point is reliable, and this has to do with the autocorrelation. If the terrain is very complex and the autocorrelation is very short, the range of validity of your observation, the scope of validity in space is very, very small. So as soon as you move out, the information becomes informative. So you can interpolate, but you're interpolating with a number that you may as well just like put in a random number, right? But if the autocorrelation, and this is what happens in flat, gentle areas, is very strong, right? Information that is 2 miles away might still be very good to inform of the precipitation change here, right? Because both points are autocorrelated. So yes, and this is what we do here. the thing is, most of the interpolations do not use like all the physics that WRF uses, right? And this is for operational purposes. So yeah, BAYESIAN uses topography, right? And it's not just like a regular interpolation. It uses topography. But again, you're relying on observation, and you have more information about what is happening at the bottom of the mountain than what is happening at the top, right? So when you're like, when you're extrapolating lapse rates, and you're extrapolating, right? So you might be carrying the low bias, right? That you're talking about. But yeah, so there should be more research in that field, absolutely. Yeah, but that's a good point, and this is exactly our approach. We use physics to interpolate between points instead of pure statistics.